We're happy to have the speaker Vladimir Roubtsov from University of Angers, product formulas for the higher Bessel functions. Volodya, please.
Thank you. Thank you very much for, first of all, it's good evening for you and good night for me. I hope. Thank you very much for your invitation. Thanks a lot, Jan, for this possibility. This is my first experience to give a Zoom talk in United States. No, not the first time. I gave for East Coast. I gave once in Simons. Anyway, I hope the connection will be good. At least it is a IHS connection, and I hope it is stable. I will speak today about product formulas for higher Bessel functions, and this is a subject of my 2 years collaboration with Ilia from IHS and Duco and Straten from Mainz University in Germany. And this subtitle you see, it's a trick which was started in 19th century and a little bit provocative title about Kloosterman motifs. It's still something in progress and something we should understand, but it is very, very recent and modern things. So what this, sorry, I spoke too long. So what this talk about? This talk about the multiplication kernels. I will explain in a few minutes what does it mean. And this is my central object, technical object. And multiplication kernels connects different branches of classical and modern mathematics, such classical like harmonic analysis and n-valued group laws, which goes back to 70s of 20th century when they were appeared in the formal group description which Buchstaber gave for different algebra topological spectra formal group multiplication. Then recently, as I told you, these multiplication kernels became very, very close to so-called Kloosterman motifs in algebraic geometry of finite fields and number theory. And of course, the main origin of the interest to multiplication kernels, it is mirror symmetry, Landau-Ginzburg models, and motifs related to Calabi-Yau varieties. So I will now go to explanation what I will speak today about. I will start with some toy models and classical n equal to 2 product formulas and multiplication kernels, so-called Bessel kernels for usual Bessel or Sonine Gegenbauer formula in the language of harmonic analysis. Then we will go to n Bessel or higher Bessel generalization of the solutions of the usual modified Bessel equation and their relations to Landau-Ginzburg superpotentials appeared in the mirror of projective spaces, the story which goes back to Givental and Dubrovin. And then I will explain briefly links to recent results and recent definitions of Maxim, Kontsevich, and Sasha Odesskii in their paper 2021. I want to say that this paper also was studied more or less in the same time, and in principle, in Selecta, it is dedicated to Maxim Kontsevich anniversary. That's the paper I'm speaking about. And then I want to explain some results of this left-hand side link. Results about singular loci of this multiplication formulas and their relations to Buchstaberies, multi-group, and valued groups, then relations to Picard-Fuchs equations and monogamy properties related to Calabi-Yau differential operators. It was very, very surprisingly that also there are some interesting links with the usual combinatoric problematic. So we obtained from our formulas, we obtained palindromic polynomials whose roots are real and the corresponding gamma vectors are non-negative. And this is a typical problematic of combinatorics. Such type of polynomial usually relates to some interesting geometric polytopes. I will speak about this very briefly and probably say some conjectures, which are now no more conjectures. In the last months of my stay at IHS, I proved these two conjectures of. In this paper, it is still conjectural, but now it is no more conjecture. And then I will speak just very, very briefly, maybe 1-2 minutes, about future application, possible application to Kloosterman sums, motifs, and irregular Hodge. So let's start with toy models and definitions. The working definition which I will use in my talk about multiplication kernel is the following. Let's suppose that we have some solution of linear differential equation phi of x, and taking the product of this solution in two different points, x and y, we suppose that there is an integral representation of this product with some kernel, sorry, this one. And this kernel doesn't depend too much on, say, accessory parameters possible or spectral parameters related to these solutions. And
Volodya, you already mentioned said too many unknown words.
No. I just want.
Yeah, it's sort of a working definition. Yeah, all right. So will you dealing with equations with analytic, algebraic coefficients?
I will give you explicit formulas. At the moment, it is just you should just draw attention that you have integral representation of products of solutions.
Listen, there are many classes of differential equation, even of linear. So then I'm asking, I'm within algebraic geometry or not? For example, you write some kind of, you see, integral dz over z, which I assume that everything is in complex domain or what?
Yes, it is. It is just one of the possible way to express this product via Cauchy type formula. Yes. So we have some integral transformation.
All right. So phi of x is a solution of
Of some differential equation, just
with complex analytic coefficients or what?
In principle, it will be holomorphic solution. In principle, in my talk, I will consider analytic solutions.
All right.
Okay. Why it is natural?
Yes, sorry to interrupt. So can I interpret that integration is an integral equation for this function phi?
Yeah, it is linear differential equations of, for example,
Uh-huh.
typical example which I will consider in this talk, and it will be only example. It will be Bessel equation and generalization of Bessel equation, so-called higher
No,
order.
he asked a different question, but Zhongzhu, so it's different. You have some differential equation, all right?
Yeah.
Probably with regular singular. Then you take two solutions and instead of
And
add
then you
them,
can find the kernel to express the
you
product in
multiply
zero.
them
Mhm.
and
For
you want to
example, the typical situation, I have eigenvalue, eigen problem, and I have a solution with the same eigenvalue, and I take this solution which depends on the some parameter which is eigenvalues in different points, and my kernel, this kernel, it is important, will not depend on this eigenvalue. You will see it just. The simplest example, of course, this product of two exponents. How to
Mhm.
present product
So
of
let me also quickly clarify. And when you do this integration on a curve, so mostly you will choose a circle, for example. And do you want the zero, to be inside of the circle, or you just arbitrarily take a
no, no,
cycle?
of course, it is some kind of Cauchy type formula. So z inside, of course.
Okay, I see. When z equals zero, that's inside of the.
Yes.
Okay,
It,
thank you.
you will see the typical kernel, the simplest kernel. It is of course delta like kernel. For example, if you take two exponents and you have a product of two exponents, you see
Mhm.
that exponent of sum can be written in this integral form with a kernel which is rational kernel. You see, 1 minus x plus y over z. So it is just the denominator, if you write it, it is just conditions that z equal to x plus y for corresponding delta kernel, you see? And I can interpret it naively like additive law, that z is the sum of x plus y. And I want to generalize it for more interesting algebraic laws, and you will see how it works. The second toy example is a classical Bessel function. Under classical Bessel function, I will understand analytic solution given by this series, series x to n over n factorial in square. And now the kernel is no more rational, but it is 1 divided over square root from this quadratic expression. So this is a very simple but very nice and important function. If you write this symmetric function as a quadratic equation, for example, with respect to z, then you have the two roots, and these two roots will correspond to the two-valued group law in sense of Buchstaber and Ries in future. So main slogan which you should have in mind after this toy example. So for usual exponential, the kernel, with my multiplication kernel, reflects just additive group law. And for a Bessel function, it is will give you some two-valued group law. And for higher Bessel function, this two-valued group law will be generalized for multi-valued group law. The second interesting and important notion which I want to draw your attention in my talk is the motivic nature of this object. what does it mean? If you want naively imagine that this motivic periodic nature of this object, should I explain first what I understand under period of motive? Under period of motive, I will understand the very simple thing. If you have a algebraic differential form omega and some topological cycle gamma, I can integrate omega over gamma. And in principle, if I have a variation, for example, if I have a family of my algebraic differential form and parameter of this family vary, then I can see how this variation gives you which variation of integral with respect to variation of this differential form we can study. Typical example of such variation, of course, is the family of elliptic integrals for one-dimensional torus or higher dimensional torus integrals which appeared in K3 series lattices or in Calabi-Yau threefolds and other type of torus integrals which appeared in mirror symmetry problematic. So
what it has to do with the previous slide? You said that these multiplication kernels are of motivic nature. What does it mean?
Because these kernels, they will, it is one of our main results that these kernels intimately related to period of toric integrals.
What do you mean related? So
Related,
how?
it will be exact theorem, which I formulate a little bit later. It will be exact theorem. So concretely, I will show you.
No, but what's motivic? I mean, if you have a variation of integrals, I don't know, like family of Fanos or whatever, yeah, you can write down the kind of, it's part of the Hodge theory, all right? What it has to do, why we should multiply solutions to Gauss-Manin differential equation, why? So that's the point. That there is something interesting called multiplication kernel, but why, how it's related to motives in any sense, even in sense of integrals. Yeah,
but you will see how it is one of our results. We just
so all right, but okay. So should I wait until you say, because you announce something which will appear much later when I will forget. I will
no, you will not
forget
about, because I will go straightforwardly to this.
All right. So, but is it just for unique or whatever special differential equation, or it's a general result? Is it something general? What generality is it? Kind of.
It is a little bit an unexpected result, because the equation which I studied, equation related to my kernels, it is not typical Calabi-Yau differential equation, which typically appeared in this mirror symmetry story. But the property of solutions of my differential equations are very similar and give some interesting relations with the periods, motifs, and even combinatoric of similar type. I will just explain you in few minutes this. Let me now show what I mean under n-Bessel function. N-Bessel function is a series where instead of a square, I take in denominator degree n. This is an analytic function, and it is a unique analytic solution of n-order Bessel equation, So let's consider differential of Euler type x dx and take the equation theta to n minus x operator and take the equation which we call Bessel equation. You remember that if we take n equal to 1, we obtain exponent, which we had as a toy model. If we have n equal to 2, we obtain almost classical Bessel. We obtain modified Bessel equation after some simple change of variables. And then for n bigger to 3, we obtain some new, of course, not very new. People knew this equation, but nobody studied the kernel property of this equation. And for us, it was a kind of part of some general philosophy, which is still non-published. It is so-called part of product identities for solution of nth order differential equation correspond to what we call non-abelian theorem, which is just explained in our preprint with Vasily Goloshev, Anton Melit, and Duco van Straten. And this preprint is an initial point to study these products. This is an output of this. Okay, if we take this nth order Bessel equation, we can associate with it in usual way some flat connection of rank n with this matrix in Frobenius type. And this connection people call Bessel-Kloosterman connection of rank n. Of course, the regular singularity at the origins, it is very easy to study because this origin is a kind of maximally unipotent monodromy point, and it means that the solution has a very simple monodromy in this point. Monodromy contains only one Jordan block of maximal size n. And in opposite, if we take x equal to infinity, then we have irregular singularity with pure slope 1 over n. Eigenvalues are exponent times x to 1 over n. So we have some kind of Fuchsian side for this kernel, while the solutions Fn has irregular side. It is some strange dichotomy because the kernels which are represent products of these solutions, they are much more nicer than the very solutions. And now,
Volodya, I do not understand. You say multiplication kernel. Does it mean that it exists? Because so far you just explain it for n equal 2. I do not understand. For any n, there exists a multiplication kernel for solutions to this n Bessel ODE.
yes, you have for this psi, phi n, you have the same type of formula.
Maybe it's, you know better. I see it first time.
And then I show you the kernel, and that's I have it in my pocket at the moment. In principle, you have this formula phi n of x, phi n of y equals to integral of kn x, y, z phi n z dz.
And what kind of function is kn for n bigger than?
This is the most interesting part. And don't go ahead. I will show you this function, and this function will be related to this period and various funnel. I promised to say how it relates to the mirror symmetry from the very beginning. So let's consider again this theta n minus x operator. This operator, or n-Bessel equation, of course, intimately connected to Giventhal's approach to mirror symmetry of projective space. You remember that usual cohomology of a projective space, it is a polynomial quotient by condition Pn equal to 0. And deformation of this quantum cohomology can be interpreted, the relation in this quantum cohomology can be interpreted like a symbol of my n-Bessel equation. So the first interesting example, if I take the Landau-Ginzburg polynomial, which depends on parameter small x and n-1 variables big X, then the solution of this equation can be written as this oscillatory type integral, exponential of Sn with toric measure like this, integrated by one-dimensional torus with this coefficient. So this is well known.
Well, maybe well known for those who knows, but this phi-n is different from Bessel function on the previous one, which you denoted also as phi-n.
No, this is my solution of my equation, this equation.
This equation, very well. Now, I mean, this equation well exists without multiplication kernel. What's the role of multiplication kernel? You said it the relation to mirror
kernel gives
symmetry.
you a family of such exponential integrals, oscillatory integrals.
What do you mean? You wrote the integral without any multiplication kernel. It's just a formula. That's it. What's the role of the fact that you can multiply?
This formula was written by Givental, I want to say.
No, all right. So then what?
But it is just an example of this solution. Now I want to take the products of this phi n, and I relate the products function of another number of variables. First of all, 3 variables in P2 and 4 variables in P3, and then in Pn-1 I will show you multinomial kernel. Interesting answers.
Does this multiplication form of the product multiplication kernel is useful for mirror symmetry, which you mentioned several? It's just the integral, you know. You have some quantum differential equation. There are tons of them, and sometimes you can write down explicitly the answer. But if you have this multiplication kernel, does it help you to understand anything about mirror symmetry?
Yes, you can play the same game like people play, for example, in the approach of Candelas, De La Osa, and co-authors, and you can find mirror coordinate, Yukawa coupling, and
yeah, I can, but what it has to do with multiplication kernel?
It gives you new type of instanton numbers.
Really? So
some of them have interesting integral sequences which some of them known for OEA's catalog, and some of them not. And these interesting combinatorial properties also are new. And also this might be useful, as I told you, for future relations with so-called Kloosterman sums. It is exponential sums over finite fields, which are analogs of these N-Bessel solutions. So you see this Landau-Ginzburg potential, and you have exactly similar Landau-Ginzburg type polynomial and the exponential in the Kloosterman classical paper 26. And the property of these Kloosterman sums, they are very similar in some sense to properties of these N-Bessel solutions. That's why it is interesting. Very recently, also people who studied elliptic and more complicated solutions for so-called Bessel momentum problem, about which I will speak a little bit later, and compute Feynman type integrals for special graphs, which called sunrise or banana graphs. They are also explicitly coincide with formulas which we obtained for Bessel functions of higher order. And this is also interesting link to study. For example, we can integrate, well, we can evaluate some Bessel Feynman integrals, which people, of course, knew before us, but it is a new representation. And because I just absolutely unable to mention all possible application in one talk, there is another branch of applications. Okay, what is interesting? Now it is interesting to say a few words about the interesting hypergeometric origins of our multiplication formulas. Let's consider diagonal x equal to y, and instead of product, let's consider the square. Then the square of 2 Bessel, it gives you a very interesting series, which first was computed in 1828 by Clausen. And this product, it is just Hadamard product of two series. And on the level of convolution, on the level of integral, it is just a convolution of our solution with this function 1 over square root of 1 minus 4x over z. And this function is generating function of so-called central binomial series. The square of 2 Bessel in its turn is a solution of third order linear differential equation, which is a symmetric square of 2 Bessel. And this also very important observation, because the Kloosterman sums in number theory, they are also reduced to symmetric powers of Kloosterman for coinciding arguments. And this is toy model for study this property of Kloosterman sums. Now, interpretation. It looks trivial, but gives some non-trivial observation. the initial formula for n equal to 2 with explicit kernel, you remember I showed you this conic x squared plus y squared plus z squared minus 2xy plus xz plus yz. This is a very, very important function. This function appeared independently in theoretical physics of 80s, so-called Kjellin function. Kjellin is a Swedish physicist, one of the founders of Central European of nuclear research in Copenhagen, and then it moved to Geneva. And Kjellin introduced the propagators for free particles. And in his book on dynamics of relativistic particles, he introduced this function, which physicists call now Kjellin function. And this Kjellin function, of course, people also know as a square of triangle area multiplied by 16. And all of these elementary objects enters as a kernel for a product of two Bessel functions. And it is not so exciting, but it is example of very general phenomena, which was probably discovered by Gelfand and Berezin in their paper of 56. And this paper considered so-called Gelfand pairs, which now people call Gelfand pairs. This is a Lie group G with the subgroup K, which K is a compact subgroup, and G is a real subgroup or complex. Then the corresponding, the Gelfand pair, it is such pair of G and K that quotient G mod K is a symmetric space. And then the product of spherical functions corresponding to Gelfand pairs, it is integral over this symmetric space of the same function with some measure, and this measure is defined. This is my Protor kernel, for example. For the case of n equal to 2, you should take Hermitian matrices H2 and compact K unitary 2 times 2 matrices, then the corresponding G mod K will be R2, and the Sonine Gegenbauer formula is just a product of this spherical function, which correspond to this elementary symmetric space with rotational invariancy. I think that, Jan, you should also know similar formulas probably for the case of Q-spherical functions. I don't know if you consider these products or not.
Well, we certainly did not consider multiplication kernels at
Multiplication
the time.
kernel is not so evident.
But basically, yeah, you take some eigenproblem and you multiply eigenfunctions and look for the kernel, but I still kind of do not understand what they're useful for, except of the question that they exist.
No, first of all, it is beautiful, I want to say. If we take
Yeah, besides of that, yeah, they're beautiful, but what you can do with that except of looking at, say, they're beautiful. See, are they also useful or they're beautiful? You know, it's kind of...
Now, instead of considering product of two Bessel functions, let's consider product of three Bessel functions. Then we have interesting elliptic family behind of this in the kernel, and the corresponding product, it is classical result. You have this product of 4 with this measure TDT, and this product of 4 gives you a very nice elliptic integral, which also depend on this parameter A1, A2, A3, and this kind of product of Bessel integrals, it appears, as I told you, in so-called banana graph Feynman integrals. For example, K3 surfaces for m equal to 4, they described by Blocher and Van Hoff, and Müller-Stach and Weinzer, they discussed two-loop sunrise integrals, these Feynman diagrams, and general M Calabi-Yau motifs, they were considered in papers of Albrecht Klemm and Claude Dur, and that's also
Yeah, but still, I mean, there are, of course,
motivation.
There is a mixed Hodge structure behind Feynman integrals, and Sasha Goncharov told me that they even able to compute the answer just from the fact that there is a mixed Hodge structure, and so you can decompose motif into some whatever sum of simpler motifs and so on. But what's the role of multiplication kernels in this?
Sometimes multiplication kernels also gives you some information about the Hodge variation of Hodge structure, and I will speak about this as well.
Okay.
Okay. Another motivation for us was, as I told, Odesskii-Kontsevich multiplication kernel paper. Among the beautiful results of this paper, Odesskii and Kontsevich proposed some answer for any hypergeometric equation, and for any hypergeometric equation of order 3, they wrote the corresponding kernel for products of solutions. It was not trivial and very nice interpretation of multiplication kernels, which appeared in the paper of Odesskii and Kontsevich. Also, the interpretation of this kernel like a kind of associative algebra structure constant, which can be completely interpreted as a structure constant, for example, for Hecke eigenfunctions for model, which Maxim considered in 2007 paper.
So say it again, what can be interpreted as structure constants?
These multiplication kernels.
Well,
yes, Maxim in 2007 paper, and which was published.
Yeah, I know that paper, but it's something about Hecke operators, yeah?
Yes. Yes.
But Hecke operators, it's, it's you have, like, you can use a kernel, like, forget about Z, KXY, you can use it as a kernel, as it should be, of an integral operator. And that's a kind of thing. So you have an operator and you can define something and you can ask whether they commute and so on, so on. Then you get Hecke algebra. Yeah, but the kernel...
But you can also compute a number of Hecke, you can compute a number of Hecke operators using it, if you take finite field version of local system P1 minus 2 points or PSL2 or functional fields or finite field, then this kernel enters the way how to compute the...
all right. You can indeed you can compute something like
Yes.
eigenvalues,
Exactly what this is a
composing the correspondence associated with that kernel. Ah, good. All right.
It is even we can say even more. Let's consider the following situation. Let's take a cubic F, monic cubic, and then, oops, sorry.
No, it's okay. We can remember cubic polynomial in one variable.
Yes, and then you take this cubic minus the factorization with three roots x, y, z. Then the being monic, t cube eliminated, and you have a quadratic equation with respect to t, and discriminant of this quadratic equation gives you exactly the kernel like we had before, which entered in this computation of Hecke operators. And over C, exactly the same answer was obtained by Frenkel, Kazhdan, and Ettinghoff when they wrote the product of Hecke operators. Now this is an operation. They are not functions, they are operators. It's Hecke operator in some Hilbert space. I don't want to precise this Hilbert space. It relates to half densities and etc. But the discriminant is exactly the same kernel like it was in Kontsevich paper 2007, but with coefficients depending on these parameters of cubic A, B, and C. What is interesting that what differential operator behind all this? The differential operator behind all this, it is Hoyne operators. Hoyne operators. If you take your cubic F and take dfd minus lambda, minus plus f prime d plus some constant, and this operator you apply to some psi, then this psi lambda, they exactly have the kernel of this dz over square root of delta PABC. So the Hoyne operators, and this was considered in this preprint, which still non-published, with Melit, Goloshev, and Van Straten, the relation of Hoyne operator and this Kontsevich observation. Okay, now, Jan, this is what I promised to tell you. Let's consider the multiplication kernel for phi n. This multiplication kernel has the following series in three variables, x, y, and z. And you can represent it in residual form with integral over torus if you have this choice of Landau-Ginzburg polynomial in denominator. Z minus product of 1 plus yj times x plus y over product of y. And then this is exactly the multiplication kernel for products of phi n, phi n. I will skip the proof, though proof is quite straightforward, but very nice. It based on so-called constant term residual computations. And then I just show you a few consequences of this formula. what is a singular locus of this kernel? K and X, Y, Z. The singular locus has the following form. We prove it with Duco and Ilia. It is kind of factorization of linear forms in U, V, and W, where U, V, and W, it is a Kummer-Lift of X, Y, Z. So we have X equal to U to N up to sign, Y, V to N up to sign, and Z, W. Then the singular locus is a product over square roots of degree n of from 1, and this linear forms with coefficients over this square root lattice. For example, for 2, this is my Cherin function. For delta 3, it is this cubic, and this cubic, it is everybody immediately can verify that this is a AGM equality condition. And as a curve, it is a curve in P2 with coordinates x, y, and z. And this curve is a nodal curve. Of course, here is one node, 1, 1, 1. But for n equal to 4, we have 3 nodes, and these 3 nodes, they are in a cyclotomic field q square root of 2. They are 4, 1, 1, 1, 4, 1, and 1, 1, 4. And the general theorem that all for this delta n nodal point, they are in a cyclotomic field q cos p over n. And this is a quite nice observation, because it means that this singular locus is a discriminantal type, and this discriminant can be written explicitly. The next theorem, that there is a polynomial of degree 2 times n minus 2 in T. And if we compute the discriminant in T of this polynomial, we obtain exactly this discriminant locus. And all this observation looks like just a game, but it is not a game. It is algebraic law of multivalued groups, which Buchstaber and Ries introduced in 1997. Let's consider the two-valued group, where two-valued multiplication, it is a law to two elements, x and y. This law corresponds to the two-set value, z1 and z2. And you remember the square roots of this quadratic equation in z of this Cherin function. Square root of x plus square root of y in square, and square root of x minus square root of y. This is exactly the definition of this law. Of course, I have no time to verify all properties of this beautiful two-valued law, but this not only discriminant, but it is also a determinant. You can represent this law in determinantal form, and this is an important point when you apply generalization of this law to computation of, for example, finite integrals. So this Chelan function again appeared, and Chelan function relates to Bloch-Wigner logarithm. This is again another story which I have no time to discuss. What is the n-valued generalization? N-valued generalization, it's our polynomials in this delta n, which gives you n set element to a pair of x and y. So, and all this law, they satisfy some subtractivity, they give you some kind of inversion and some kind of natural element. And geometrically, it means that we using this Kummer lift, we have a lift of law on the C star, which is just an abelian law. And then we lift this law on the n-fold cover. And this n-fold cover gives you law on symmetric degree of C. Well, as I told you, the rational curve in P2 has some double points, some nodal points, number of nodal points n-1, n-2 over 2, and all of them are in cyclotomic field cos P of n. The same, almost verbatim, but much more technically complicated principle can be applied to the product of not two, but m Bessel functions in variables x1, xm. And you have a multinomial kernel. This multinomial kernel is even much more interesting because this multinomial kernel can be computed. We compute them for any m, and they have a form very similar to so-called LGF, lattice green functions, which correspond to some random walks on over some multidimensional lattice. And they are not coincide with this LGF, but they relate with LGF by Borel transform. This is not yet written, though it is proven. And geometry of these multinomial kernels, even in our paper, verified with the following application to geometry of so-called Hulik-Viril varieties. These Hulik-Viril varieties, they are family of varieties of this type, and they appeared in these many loop banana graphs. For example, two loop banana graph correspond to Hulik-Viril with m equal to 3, and case 3 loop to m equal to 5, etc. Our theorem will apply to these Hulik-Viril varieties, and we obtain some period related to these varieties for m equal to 5. Okay, so this I told you about this principle of demonstration. It is a constant term residual formulas. And then we can consider the same formulas residual formulas on diagonal. Let's take all x equal to y equal to 2. Then my polynomial, it is a special case of polynomial Wn, which appeared in the first formula, you remember, and exponential integrals relate to this Vn for diagonal as well. So we have some family of hypersurfaces, dimension of this family n-2, and Gauss-Manin system gives you Picard-Fuchs operator in one variable. And then let's see what's happened with these Picard-Fuchs operators. First, if we take n equal to 2, we have operator order 1. I remind you that theta is a t d over dt. And then this operator annihilates the kernel of degree 2. This is the operator which annihilates K2. This operator annihilates K3. What is interesting with these operators? The interesting with these operators is the following. This always singular point is at the origin, t equal to 0, and up to n equal to 5, it means order 4 differential operators. Origin t equal to 0, it is mum point. It means that the Jordan block is only 1. Interesting that for the case n equal to 5, the corresponding operator, which too long to be written here, but it is possible to find in the catalog of Calabi-Yau operators. Its Calabi-Yau operators relates to Picard-Fuchs of Calabi-Yau threefold. But if you take n equal to 6, then the next differential operator which annihilates the kernel, K6, is no more mum at 0. It's no more one Jordan block. It is Jordan block of size 5 and 1. So one-dimensional block appears at 6. And then computation shows that with the growth of n and growth of degree of my differential operators, we have some periodicity, we have some four-step growth. It means that number of Jordan blocks which appeared for n equal to 6, 2, for n equal to 10 becomes 3, and for n equal to 15 becomes 4, and etc. So there is a conjecture that if we have this t equal to 0 and Jordan blocks of my kernel for equal bigger or equal to 6, then the number of Jordan blocks is n minus 1 over 4 integer at least, and the size of blocks n minus 1, n minus 5, n minus 9, the next n minus 13, etc. And it is interesting that how this Jordan block structure relates to middle Hodge rows in Hodge diamonds, so to Hodge structure. If you have mum, then of course this row for n equal to 5, 1, 1, 1. For 6, you have this 5-dimensional block and 1-dimensional block. You have 1, 1, 1, 1, 1, and over this, you have 0, 0, 1. So in the middle, you have 2.
So,
So-
Volodya, first of all, I do not see the whole page. It's, at least for me, yeah. Now it's better. Second, I see that you kind of spoke about 2/3 of your slides. So how much time do you need?
Well, it depends how much time you have.
No, I
suppose-
mean, it's
suppose
normally it's talk, it's 1 hour plus epsilon. So
you
you
know
can,
that well, okay. It means that I can just finish with this because
and maybe some conclusion, you have time for whatever concluding remarks, because the fact that you give another 10 formulas, it will not make at least me happier. You see,
no, it means that this is just a conjecture, which is not so evident, but it is even for 6 and 7 and 6 and 7. This conjecture, how it relates to these Hodge patterns, you should compute so-called Steenbrink weighted spectral sequence. But for it was done. I did it for 6 and 7, and I'm pretty sure that this conjecture can be proved in general. And it is just a technical thing with a mixed Hodge structure and Schmidt-Steenbrink spectral sequence. So it is described completely. You can ask why do you interested in this? The answer is the following. I want to have some kind of enumerative invariance like in mirror case. For example, for the case of n equal to 5, when I have mum, I can do the same things like it was done by Candelas and co-authors, and define this Yukawa coupling and obtain integrality condition and obtain a kind of instanton numbers. For some deformational parameter, I obtained many interesting new integer sequences which are unknown for OEs. But if you take initial parameter, you obtain Catalan sequence. And it is a very nice and surprising answer. So this multiplication kernel geometry gives you a classical enumerative sequence. This was, I think, very nice. Okay, then we were inspired by this, and considering another combinatorial property of our kernels, not for diagonal, but for any x, y. And then we obtained some theorems about palindromic polynomials, and also established some relation between our kernels, Landau-Ginzburg superpotentials, and so-called Dwork polynomials in Pn-1. They are intimately connected by some limiting procedure. It means that we can obtain results for Dwork family as a limit of our computation results. For example, we can obtain generalization of Catalan and Narayana numbers. Okay, so I skip the what I promised to say about these Kloosterman motifs and Bessel momentum. And then I just only show you that our formula gives you exact so-called Van Hoff formula for Hulik-Veril general polynomials. The difference between Van Hoff formula and our formula is that we need to make a change of variables to change the integration cycles. And it is quite amazing that for n equal to 2 and for n equal to 3, we can do it explicitly. That's the last picture which I want to show, that in one hand side we have in the regular side n Bessel equation, oscillator integrals of this type, quantum cohomology, and irregular Hodge structure in the computation of these oscillator integrals. But if we go to kernels, we have Fuchsian, we have Picard-Fuchs operators with Fuchsian as singular points for kernels. We have Landau-Ginzburg models and torus period. And we have new mirror map and Calabi-Yau type operators. And our Hodge structure is regular. So we have some two pictures
yeah, but it's not clear, at least. For example, let's take the last line, irregular Hodge structure. All right, so yeah, I know what is it, but what it has to do with multiplication kernels?
But multiplication kernels, they
What
satisfy.
irregular Hodge structure in what? In abstract sense, in a particular example, or what?
In irregular Hodge structure appeared when you try to study this type of oscillatory integrals. And then the jumping
So
is
it's a regular Hodge structure for some
in sense of
for oscillator integrals, yeah? Oh,
yes.
all right, so that's not just abstract story, all right. And
No,
then,
no,
okay, so that's
everything is quite concrete.
at least not on your slide, because irregular Hodge structure, it's quite a subject. Quantum cohomology, well, of Pn minus 1, it's very particular quantum differential equation, but maybe you
I want to say
have
that
in
it is
mind
if you
something
want.
about more general Fanos, because Pn minus 1 is just
No,
an
no.
example.
Yeah, I understand. Bessel story, it's a story of maximally degenerate flag. But if you replace this Kloosterman Bessel connection,
Yeah, you have partial flex. This I understand. It's also
very partial.
Givental.
But you can consider as well so-called Gross-Frenkel connection. And for Gross-Frenkel connection, you can try to do the same story with
No, again, it's a question about generality, because Gross and Frenkel, they did it for an arbitrary reductive group G. And
no, you can
I think you do it for GLN only.
There is a mirror program for any parabolic group, G mod P, and the so-called Lemon-Templier. And that is, basically, it is only one part of this program.
Okay, maybe. So but the bottom line is that if you have some kind of, I don't know, periods or whatever it is, motives or just oscillatory integrals. So if you do have a multiplication kernel, then it's kind of a simpler object because it has regular singularities.
Yes. One can say this.
Yeah, all right. And the algebraic structure, like, this, after all, multiplication kernel gives you a sort of, as you said, structure constants for some, whatever, algebra. If
Well,
you
and valued groups, or if you want, you can consider hypergroups. You know what?
yeah, if you have, not just
Yes, it's a
methods,
hypergroup. Yes.
higher tensors. And
Either
this,
or if you want co-algebras of function, commutative co-algebras.
Okay, and this algebraic structure is just present. It's a way to say nicely that your kernel satisfies some relations giving associativity and
Yes. We wrote a paper with Buchstaber and Ilia about the relations between multiplication kernels and these
formal group laws
formal
general.
and groups in the first issue of Известий.
And open questions. Maybe you say a few words about
Open questions, yes. This monodromy conjecture, of course, it was a kind of challenge for us because Duco, who is big expert, was not able to do it. So I decided just to compute n equal to 5, n equal to 6, the first two, n equal to 6, n equal to 7, the first two non-trivial cases of non-maximally unipotent cases. And I tried to recover these patterns from variation of Hodge structures. And I was very much surprised that if you take this Steenbrink-Schmidt spectral sequence, then from computation of first term of this sequence, you obtain immediately this patterns n minus 5, n minus 9. And so I'm pretty sure now that if I compute the spectral sequence, the E1 term for any n, then I will prove my conjecture in full generality. In contrary, the positivity of gamma vectors and the realness of roots of polynomials which relate to my kernels in different representation, I proved. And what I don't know if they are relate to some interesting convex polytopes. I have found some polytopes, but I didn't find how much they are interested in this. That's a problem. Anyway, and the question of non-rigid system. It is not my area. I don't want to discuss it because it was Ilia and Goleshov who are responsible for this. So
yeah, but I'm not just to understand what you're talking about. So for rigid local systems, like there is this CATS middle convolution algorithm. What it has to do with, I mean, are these kernels, because it's convolution, it's a sort of convolution in the middle cohomology.
yes.
So this your multiplication kernels, how they're related, they're objects which realize the Scott's middle convolution transformation, or what? How it's reflected that you have some local system, all right? You can, as you said, you can take some solutions to the corresponding differential equations. Let's forget that it was Eliadic, and you multiply them and write with as a multiplication kernel, and it's somehow related to this Katz middle convolution kernel. So I'm thinking in the wrong direction.
I have no idea. I don't want to speculate about it because this you can ask Ilia. Maybe he will say something because they wrote, and I don't want to. It's a kind of, you see.
Yeah. All right. Okay. So then
I didn't discuss it. They started to discuss it between them, and I decided not to go there. That's all.
All right.
Oh, in contrary, I was very interested to consider this periodic integrality, and at the moment I'm able to write some kind of product of two Kloosterman sums of rank 2. But it is trivial, but it is interesting. And it is interesting because there are some periodic analogs of hypergeometric functions, and degeneration of hypergeometric functions like this 0, 1 convoluted hypergeometry from Gauss in the periodic world is highly non-trivial. And well, it is interesting to think about it, but you know, I discovered the whole new world for me, and I stopped to think in other things, to think about other things, and
Yeah, all right. So maybe we should somehow wrap it up. Are
so
there
there
any?
is if you are, I,
Yeah, on the slides which are in the chat. So maybe one question from the audience, because we are kind of quiet over the time. Are there any questions? Well, if not, then Volodya, thank you for your talk. It's more questions than answers, but people can look, for example, on this Kontsevich and Odesskii paper, which is called multiplication kernels, and there are more motivations for the general topic.
oh, there is a general motivation which, of course, I have no time because it was not related to Bessel, but in fact, it was related to my old paper with Enriquez about separation of variables for Hitch.
For Hitchin. Yeah, yes. It's
Yeah,
indeed old paper with Nikita and many other people.
yes, yes. This is what I want to say. There
Okay.
is an interesting link. There is some kind of multiplication kernels related to multi-particle systems, like Roisinas or Calogero and Sklyanin. And uh, I forgot his name. Not he was student of Komarov from Leningrad. He, Vadim Kuznetsov. Sklyanin and Kuznetsov, he committed suicide. The guy, maybe you don't remember him. He was
I don't know.
he was in UK, and it was a strange case. He was professor in Leeds, and he committed suicide, Vadim Kuznetsov. But they wrote few papers about Roisenars A2 and Kalodjera-Moser A2, A3, where they wrote some kernels, multiplication kernels, for eigen values of quantum problems for this. You see?
Yeah, and in the end, they want kind of
And it was a kind of separation.
commuting Hamiltonians.
Yes, yes. Separation of variables, like we argued with Benjamin, and Maxim and Sasha also have the same philosophy.
All right. Okay. Thanks again. And well, this is it. This is it for today.
I'm sorry if I was not
No.
able to answer all your questions.
Well, the main thing is that you became interested in the topic. That's at least what the speaker should do. I mean, we shouldn't know everything and learn it by heart, but if it's interesting and there is a lot of reading. All right. Well, thank you. Thanks, and thanks for those who came for this talk. And this is it for today.